Mathematica. And if you're wondering, what on earth am I finding when I get a directional derivative? This is what you're finding. Right. I want you to imagine that you've got a surface. Oh, are you seeing a big green blob and it says sine x minus y? Are you seeing what I'm looking at on my second screen? Good. Okay. So imagine this is your function. And you want to know a directional derivative to this function at a given point, x naught, y naught, just right now it looks like it's the origin. It is. And going in an angle of, in this case, 2.9 radians. So imagine that's the point that you're interested in. If you go to that point, maybe I should hide all the other stuff for a minute. There we go. Do you see on the surface, if I rotate it, can you see that point on the surface? That's it on the ground. The dot is the point on the surface. Right, that point there. Now, if you do in the direction theta, you cut the shape in direction theta. So for instance, if I move this around, can you see the direction on the ground cuts the surface vertically at a particular angle? Now, when you cut it at one particular angle, do you see that red curve is the intersection of the direction with the plane? And do you see that point is on that red curve? If you find the derivative, which is another form of the tangent, you make that blue line. The slope of that blue line, that number, right? The slope of that blue line is what a directional derivative is. So can you see at that point on that surface, if you traveled in the direction theta, the blue line would be the angle you'd be climbing uphill. So at that point, the surface is quite steep, right? Of course, if I move the point around a little bit, there. Would you agree at that point, the surface is almost horizontal? That would probably be at the, you know, the part of a hill where it curves around like this? You'd be right at the top. Now, if I orientate it differently, there. Well, it's not quite horizontal, but if I tweaked it a little bit, wouldn't it be horizontal? So when you're thinking about what is this number 4 or minus 4, right, or 0, this directional derivative, it's the slope of the curve on the surface that you would get in direction theta. Visually, it's that guy in front of you, right? So hopefully that, for those people who are visual and like to know what you've just found, that's what a directional derivative is. Does that, for some of you, does that help you visualize what you're getting? Now, for some of you who don't really care, I guess it doesn't matter. It doesn't change how you get the answer. It just means you get the answer. So let's do some practice on directional derivatives. I'm calling this one version 1. So find the directional derivative of this function at this given point in the direction theta equals pi upon 4. Well, in this case, you get the direction, which is a unit vector, and it's going to be cosine theta, sine theta. And in the first quadrant, the cosine of pi upon 4 is that, and the sine of pi upon 4 is that. And remember remember on Friday, we did the unit circle on the table. You gotta know exact values of standard angles, you know, like sine of phi 6 pi and cosine of 3/4 pi. So that's my unit guy. The gradient vector is the partial derivative with respect to x and the partial derivative with respect to y. In this case, if you do the partial derivative with respect to x, you get a product rule. So it's f dashed g plus f g dashed. And then you differentiate this, and you get negative, two negatives make a positive, so positive y sine x. And then you differentiate it with respect to y, and you get a pretty boring cosine x. And that's called the gradient vector. Now I'm going to evaluate the gradient vector at this point here. So it's going to be the sine pi plus pi cosine pi plus pi sine pi, comma, negative the cosine pi. Let's see what we get. Sine pi is 0, cosine pi is -1, so that's negative pi, and that's 0. So this guy is negative pi. And the cosine pi is -1, so the negative of -1 is 1. So here is the directional derivative evaluated at that point. Sorry, this is the gradient evaluated at that point. The directional derivative of f at this point is the dot product of the gradient vector and u. And the gradient vector is that guy, and u is that guy. So what does that get me? Negative root 2 upon 2 pi plus root 2 upon 2. That's good enough. I guess you could pull out that, make it look slightly prettier, but it's correct in both cases. Are we comfortable about the mechanism of how you find the directional derivative to a function at a given point in a direction theta equals some angle? And this is essentially the process that you do. The only thing they're going to change, angle's going to be different, that point may have a different coordinate, and certainly this function will change. But not the process. Won't the process remain exactly the same, just for different numbers, different functions? Have we any questions about that particular guy? Are we good? Okay, let's do a version 2. It's still going to be find a directional derivative, but this time you won't be given the angle theta in which the direction is described. Instead, you're going to be given a vector v. Right, so it might be in the direction 2, 1, or something like that. Right, so let's have find the directional derivative of the function. Let's have x e to the y plus e to the xy. And we want to find it at the point 1, 0 in the direction 1, 2. So the major change here is that the direction is no longer given in terms of an angle theta, but given in terms of a two-dimensional vector. Now, when you have a situation like this, and can anybody remember what we do to this vector here?
Turn into the unit vector.
Right. So we find its magnitude, as someone else was about to say, and you're right, G, you find its unit vector. So the magnitude of this vector is the square root of 1 plus 4, which is the square root of 5. And so the unit vector is basically 1 over root 5, 1, 2. And I'm just going to leave it like this for a minute. I'm not going to, I could bring in the root 5 and there would be nothing wrong in doing that. I'm just going to leave it in that format. Now, if I find this fella, partial derivative with respect to x and the partial derivative with respect to y, I will get, for this fella, e to the y. And what do you get when you do a partial derivative of e to the xy with respect to x? You don't just get e to the xy, do you? What else do you get?
Y e to the xy.
Agreed. Then you do comma, and then you do the second fella. Only with respect to y, this guy is him. And with respect to y, this guy is him. So you can imagine, just by the week that we've been doing this for, aren't you going to be probably doing lots of partial derivatives? So you'll get really good at them. Well, hopefully you're already really good at them, but you get lots of practice if you are. So this fella is going to be evaluated at 1, 0. So that's going to be e to the 0 plus 0 times, I don't really care what this is. I'm putting a 1 anyway. Well, actually, it's a 0. Comma, 1 times e to the 0 plus 1 times e to the 0. And this guy is 1, and this guy is nothing, and this guy is 1, and this guy is 1. So it looks like the answer ends up being actually quite a nice answer. 1, 2. Now, you know I can't count, so if something is wrong, this is your time to tell me. If it looks good, then I'm going to keep going.
Looks good to me.
Let's keep going now. So the directional derivative of u f at the point 1, 0 is the dot product of the gradient vector at 1, 0 times u. So it's going to be the dot product of this vector. Oh, would you look at that for coincidence? I never noticed that until I wrote it down. By sheer total coincidence, no other reason, aren't those two vectors the same?
Indeed they are.
I did not plan that. Do not make any assumptions that they should be, right? In fact, if you think about it, aren't there an infinite number of different answers? And that's much more likely than the same answer. Well, I put it together. I get 1 over root 5. Kind of suck that out and then just do these dot products. Oh, that gets me that guy, which if you rationalize the denominator, whoa, that is such a cool, nice looking answer. I wish I could have told you that I planned it that way, but it's not. Can you imagine situations where the dot product of these two could be 0?
Yeah, if one were negative, right?
Can you imagine? Yeah. Yeah, if one was, negative and the other was positive, whatever. Right, you could get a 0 out of this, couldn't you? Maybe not this combination, but there are combinations out there where 0 could happen. And if you're wondering what does that mean, can you imagine that you've got a hill? It's a good analogy. On that hill, isn't there a kind of horizontal belt where you don't change height? Like you walk sideways around the hill. The directions that make that sideways happen all have a directional derivative of 0, and they're not the same vector. Can you imagine the vector's here, then it's here, then it's here, then it's here? Can you imagine as you go round the circle, won't the direction that you're traveling be a different direction, even although the directional derivative is horizontal, right? The direction, right, the theta guy, whatever you want to call him, he will very often be different. That would probably be an interesting point on a surface, wouldn't it? All the points whose directional derivative were 0. Wouldn't that be an interesting sequence of points on a curve? Do you know all the points on a surface that have a directional derivative of 0? If you've done anything in maps, you know what they are. Can you imagine that's a contour map? All the points on a contour map that are the same height are joined together, right? So you can basically say that's a little funny hill, right? Do you know that every single point on, say, a height of 10 meters, every single one of them, won't have a directional derivative of 0? Because at that point, as you're going round that hill, pointing in a certain direction at least, shouldn't you be able to go horizontal? So if someone gave you a three-dimensional function, and you would do this by computer, you could ask the computer to find all the different points and direction together, so it's a combination of the two, that give you 0 directional derivatives. And if you ask the computer to do that, do you know the computer would actually create a contour map? It's kind of fun. I think it's fun. So, I've given you one example of a theta. I've given you one example of a u. What do you do if the vector that they give you is already a unit vector?
Then you can just take the derivative
Dot product.
and jump right
Yeah,
into
gradient and
doing the
dot
dot
product. Yeah, I'm putting words in your mouth, but I kind of know what you're. I believe I know.
Forgot the vocabulary term, so
Yeah.
fine.
Yeah. Well, you should do what I do. It drives my sisters crazy. I forget words. I forget words even when I was young. So if I get really frustrated, rather than just try and remember what the word is, just stick in the word banana. And so you take the banana of the function and then you do a dot product with the unit vector. Now, banana is a placeholder for the right word, and hopefully people will say, oh, do you mean the direction derivative, or do you mean whatever it is? I don't know if that helps. Probably doesn't. I'm trying to move over now to the homework questions. I hope we're able to just look at these questions now. That's not, is that big enough for you to see? Or do you want me to try and enlarge that? Are we good? Can you see these questions?
Yeah.
Okay, we're going for it. Right. Can you see that questions 1, 2, 3 are all directional derivatives where they're telling you the angle? Right, so that would be my version 1 questions. And then if we do questions 4, questions 5, can you see that they're giving you a u vector? And if you look really carefully, can you trust me that the u vectors are already unit vectors? So I don't need to do anything except go straight into the calculation. On the other hand, when you get to questions like 6, 7, and 8, do you see that the vector is a v, and v is not a unit vector, so you have to do that unit vector thing. So it's still a version 2, but you have to do the whole job, right? Whereas the other one, you didn't need to turn it into a unit vector because it already is. So you might say, well, what if I didn't notice it was a unit vector? Well, once you found its length, wouldn't its length be 1? And you'd go, oh God, it's a unit vector. That was a pointless exercise, right? You would find out that it was unit, right? It would just take you 5 minutes. So I'm wanting to do a 3D version, which kind of starts around about question 9, where you're given a function, a point, and a vector direction, right? But these are given in a number of different ways. So that's kind of where we're going to go now. So we're about halfway-ish through the work in that section. So here's my first version of a directional derivative. They're like polynomials, which I'm quite happy with. So x squared plus xyz plus z cubed. You'll be given a point. Let's suppose it was a point 1, 2, -3. And you'll be given a vector in which you're going to find. So how about 1, 0, -1, right? So we are interested in finding the directional derivative of this function at this point going in this direction. And the only difference between what is happening here and what's happened before is, can you now see that there are 3 variables, right? So technically this is a 4-dimensional function. So since V is this guy, its magnitude basically ends up being the square root of 2. You okay with that? You could do it in your head, right? So the unit vector that we use in our calculation is going to be this fella. And I'm just going to leave it like that again. Now the gradient vector is going to be differentiate with x. So that's 2x plus yz. The middle one, the y, is going to be xz. And the z fella is going to be xy plus 3z squared. Hopefully I didn't screw up there. And now I'm going to find the gradient vector at the point 1, 2, -3. So it's going to be 2 lots of 1 plus 2 times -3. Gotcha. The middle one's going to be xz, so that's 1 times -3. And the last one is going to be xy, so it's 1 times 2 plus 3 times -3 squared. What does that look like? 2 take away 6 is -4. 1 lots of -3 is -3. And 3 lots of 9 is 27. So our directional derivative at the point 1, 2, -3. Oops.
Wouldn't the z be 29 because it's +2?
Did I miss a plus something somewhere?
Yeah.
I did, didn't I?
Yeah, I think
Plus
so.
2. Thank you. That's why I have students to catch me from arithmetic mistakes. Well caught. I like that. Thank you. It does mean, actually, it cheers me up. You might think, hey, how can make mistakes make someone feel good? It makes me feel good because it means that you've been paying attention and you know what the heck I'm doing. If you didn't know what I was doing, wouldn't you just be writing down any old number I wrote down because I wrote it down first, right? Which means you're not following it. So the fact that you caught that means you are following it. So I like that. Now this is going to be the dot product of this guy with our unit vector. So that's going to be -4, -3, 29 dot product with 1/√2, 1, 0, -1. And the reason I like to keep this guy kind of out of the battle is, isn't it much easier to do dot products with numbers than to do dot products with things like 1/√2 and so on? It just makes things messy. So it's going to be 1/√2 and then -4 times 1 plus -3 times 0 plus 29 times -1. That's -4, that's -29, so that's -3, -33 I should say, over √2, or that guy. So at that point on this surface, going in that direction, you're actually going downhill about, what's that, 1.4, about 20 units roughly. So it's very steep downwards, right? So if you were on the surface of a mountain that looked like this, and you walked in this direction here, you would be walking downhill in a very, very steep -10 kind of direction. So you can imagine what would that look like. Actually, since this is 4 dimensions, you can't imagine it anymore. But mathematically, we just say the rate of change of the function is -10, right? So it's decreasing at that point. Are we good? Right, so there's not an awful lot of difference, would you agree, between a 2-dimensional and now a 3, I should say a 3-dimensional, now a 4, but a 3-variable one compared to a 2-variable one. Maybe that's a better way of saying it. Would you agree? Couldn't you do a 10-variable one? I'm not going to do one, but couldn't you, theoretically, right? So if the people who do string theory wanted to know the directional derivative of an object in 11th dimensional space, which I believe is the number of dimensions that you need for string theory if you're doing a model of the universe. Yeah, 11 dimensions. Never looked into why they need 11, but they need 11. You could do a directional derivative in that, can't you? Just tell me, you know, a function, tell me a point in 11 dimensions, and tell me in a direction in 11 directions. It becomes a numerical thing, but you'll get a number. Are we good? So here's,
So
okay, let's go for another function, another 3-variable function. And I'll keep it as polynomials just to make my life easy. Here we go. And we're interested in the directional derivative at the point P, 1, 1, 3, going in the direction of the point Q with coordinates 2, 5, -1. An example of this question would be in 2 dimensions, question 11, and question 12 would be a version of this in 3 dimensions. So we have one last puzzle. How do you get a directional derivative when you're told a function, you're told a point, but you're not given a direction as theta equals pi upon 2. You're not given the direction as a vector v equals 1, 2, 3. You're given the direction as you're at P and going in the direction of another point called Q. Now I need to get a U, a unit vector, out of this information. What's your gut feeling telling me what I should probably do to make that happen?
Turn the point P and Q into a vector.
Which I hope you all remember the trick. The way I do it is second take away first. So 2 take away 1, 5 take away 1, -1 take away 3. Are you happy about how to get the vector PQ? Coordinate of Q take away the coordinate of P, right? Each one for X, Y, and Z, and that's the guy that you get. Now I'm going to call this guy V, just to make him a little bit more consistent with the rest. Then won't the magnitude of this be 1 plus 16 plus 16, which will be the square root of 33. And therefore my unit vector is 1 over the square root of 33. That one. Are you comfortable about the process, how you take P to Q, make it a vector called PQ, and find the unit vector version of that? We good? Now, the rest is pretty standard, but for completeness sake, let's do it. The gradient of f is the derivative with respect to x, which is 1 plus yz. The derivative with respect to y, which is 2y plus xz. And the derivative with respect to z, which is just xy. And now we're going to get the direction derivative at the point P. So that's going to be 1 plus 1 times 3. 2y becomes 2 times 1 plus 1 times 3. And xy becomes 1 times 1. And that's 3 add 1 gets me 4. 2 add 3 gets me 5. And 1 times 1 gets me 1. And so to get the directional derivative of f at the point 1, 1, 3, it's the dot product with the unit vector. So it's going to be 4, 5, 1, and this fella. So what's that going to be? 1 over the square root of 33. 4 times 1 plus 5 times 4, add 1 times -4, and the answer I get, I believe, is 20. Which, if we convert it, is 20 root 33 over 33.
Shouldn't the z for the gradient vector be 3?
Let's check it. The gradient vector for this one should be 3.
Oh, never mind.
And you are,
figured out. I
no,
figured
no, let's check it. It's xy.
out.
No,
Just one.
but I'd rather you check it now, but I don't mind this, G. I'd rather you'd say, hey, you think that's right, and then, oh, I'm okay, than to let it go. Because when you go back and look at your notes, if they're in error, it'll confuse you for why is that, why is that number when it should be this number, and then you kind of second guess yourself, and you don't need to, or you shouldn't need to. Do you feel comfortable about the last version of direction vectors? Right, this is kind of the ultimate of making it messy. You can't really do much about a function except give you it. And you can't really do much about the point that you're interested in. But can't we do a little bit about the direction? It could be theta's pi upon 2. It could be the vector v is 157. Or it could be you're at P, go in the direction towards Q, which is what this one is. And that's it. I can't think of any other permutations of this type of question that you could do. Any questions about this, or are we cool? I guess you'll find out when you do your homework. We find good. Okay, I like that. So let's talk about what's essentially going to happen tomorrow, because I can take my little list and check that one off. We're going to look at maximum rate of change and the direction of the maximum rate of change. So I want you to imagine that I've got my surface, and I'll make it just a nice kind of boring hill, right? And there's a point here on XY which you project up to be on the surface, right? So that would be the point on the surface that you're interested in, right? That there is a coordinates of P, but that's the point on the surface. And in this point, can you imagine that you could go lots and lots of different directions? But there is one particular direction that is the biggest magnitude, right? The biggest direction. In other words, if you were on the surface of that hill, what direction would you go to climb up the steepest, right? What would be the steepest part of the hill? And we don't care if it's steep going up or steep going down, because it's an absolute value thing. Maximum rate of change, right? And we would like to find that maximum rate of change. So you're going to be given a function. Maybe it'll be x squared plus y squared plus z squared. you're going to be given that, and you're going to be given a point P, let's say 1, 2, 3, and you're going to be asked to find the maximum rate of change, and you're also going to be asked to find and the direction of this maximum rate of change. Any ideas for how you think you might go about solving this problem? Because the solution, to me anyway, is not actually that intuitive. Oh, here goes. The magnitude of the gradient vector at the point 1, 2, 3 is the maximum rate of change. And what about the direction? The direction is the gradient function. In other words, it's dead easy to find. Because don't you always have to find the gradient direction, the gradient vector anyway, right? Well, now you know that the gradient vector, whatever that is your maximum rate of change. Its magnitude is your maximum rate of change. And the direction you go is that. And if you want that to be converted into a unit vector, which they very often do, you can get that. I would not in 100 years have guessed that that was the way that you solve that problem. It just